Hi everyone. This video lecture is going to be on BP NNA, back propagation neural network architecture. I have divided this topic into multiple sections, like part A, part B, and maybe even part C. Part A essentially covers the basic BP introduction, and then part B covers the essentially the output simulation trace, and that's very important for the tests. And so BP, as I indicated, is if you look at this network, BP is a very complex network. It's a but important thing, it's also most useful of all the neural network architectures. It's a complex but most useful NNA. What it means is complex not in terms of its topology, but the way the network is trained. Training is a little bit more complex, in fact a lot more complex than perceptron that we have seen before. However, of course, if you work out some numeric example, it is not that hard to follow. But if you try to just see the theoretical reading, that will be very hard to comprehend. But if you work out some numerical examples with it, take an example and then work out, probably that's not very hard. In fact, the way to study this network is to work out some example, then go back and try to read what those equations are. But if you try to read the equations first and then try to do anything else, that's very hard to follow. So obviously we'll be following the simulation trace. That makes it easier to understand it. Again, we want to study this network because it's the most useful network. You can solve almost a variety of problems with this network. Some of them are actually, if you go back to page, we have, if you look into this network, document networks, documents for this topic, I have divided them into 6 sections, like doc A, doc B, doc C, and doc D, and so forth. If you look at this, just a moment. As I already indicated, it's a very useful network. We want to study this network because it is a most useful network, and it can solve a variety of problems. I'm going to show you some of these, some of the applications where the BP network can be applied. If you look into it, it's on doc B, page 195. For this, before I go here, I want to indicate essentially most of the information that we have divided into 3 documents. Doc 6A has got some basic introduction to BP, network, and then 6B and 6C essentially chapter 8 of the back propagation. It is a very big chapter, so it has been divided into two documents, on part A and part B. So chapter first part of the chapter 8 is document 6A, 6B, and then second part of the back chapter 8 is going to be document 8C. So whenever I have identified indicated where the information is available, that is there, it listed as, for example, where I'm going to show you some of the examples where the application can be found. It is there on page doc B 195. What it means is that it's essentially second section of the chapter 8. And so let's look into this page. Again, if you go to page document B, and that's is the party of the document 6A. We go to page 195. And if you look at the application, that's as indicated here is BP network is perhaps the most frequently used network for a variety of applications, more so than any other network in use that is in use today. The network possesses huge modeling power due to its multi-layer and non-linear transfer functions. This vast modeling power encompasses a large set of problem domains or problem types. Most importantly, the network has theoretically sound training algorithm, which makes many neural network users confident in building NN-based application. Some of the applications where BP network has been successfully used include the data compression, the vision, 2D and 3D vision, image classification or image recognition, the synthesis, essentially the modeling of the processes, text reading, signal processing, automatic target tracking, speech recognition, and so forth. One thing that is not listed here, if I add one more, would be for process modeling, which is actually very, very useful application of the neural networks. Now what we'll see is from here, let's look into review of the application where how the network is going to be used. Now I have essentially divided this the lecture into for now 2 sections. Part A essentially covers the as we already studied, the BP is it's a complex network to plot or to map complex data measurements. Perceptron is meant for simple data mapping or simple measurements. Again, first actually we are gonna in this lecture, first we are going to look into the first the BP basic overall architecture, that including its topology, its neurodynamics, and also its training algorithm. As we already studied in basic introduction to neural networks, to study any neural network architecture, one need to study its topology, which identify how the network is formed, how it is interconnected. Neurodynamics, how the information is processed by individual neurons. And training algorithm indicates type of rules or type of formulas that are used to make network weight changes. And that's after that we are going to look into the overall BP network examples in terms of the various steps of the look into simulation trace, BP simulation trace. That is in the overall aspect of how it is implemented. Then we look into the actual training itself. Then then we also look into the overview of the BP network training, and then we look into the network how the training sequence, what are the step-by-step procedure that you would use to train the neural network. And the second section of the part B will look into the, importantly, once you understand all the basic theory, by the time we are done it, we would have understood the basic theory. And then we applied the basic theory to solve numerically some given problem. That is the actual implementation itself. You can run this using, there is a backpropagation simulation program. You can feed some information about the network, then it will generate the corresponding output simulation trace. It identifies how network is trained by a step-by-step procedure. And once that is done, once this is done, I will provide a MP4 file both on YouTube as well as on the Blackboard. I'll let you know what the links are going to be for this lecture. So now let's let's look into the basic architecture. Again, this part is there in the document B. If you look at on page 180, you can find the basic topology of the BP network. Again, now if you want to look for the overall architectural network, if you go to the page 180 of the propagation chapter, this is the overall network architecture, BP network. BP NNA architecture. It is a multi-layer network, multi-layer fully connected feed-forward network. It has, if you look at this, you would see these are the primary inputs. It can have it is a multi-layer network, but it can have any number of layers. Most of the network, the neural network that we see, they have a fixed number of layers. But by backpropagation, you can have any number of layers. What it means is all the BP networks would have one input layer and one output layer. But you can have the one or more hidden layers. You can have 1, 2, or 3, 4, any number you can have it. But the one which are most frequently used ones are either you can have one hidden layer, or at the most you can have more than 2 hidden layers. The reason actually you can have more, having more layers is not going to solve, not going to be very useful, is that we will see later on when you work out the numerical examples. When the network is trained, the network training is not really uniform. All the networks which are close to the output layer are actually trained the most. As you go towards the input layer, the amount of training done is smaller and smaller. So what it means, if you got lots of layers in between, there is no network is all the layers which are close to the input layer, they're not even going to be trained. If they're not going to be trained, there's no point in having those layers anymore. And therefore, 1 or 2 probably the most that you need for any type of applications. Almost all the applications that are implemented today, either they have used 1 or 2 at the most. I never seen any application they have used more than 2. For this textbook, in this textbook, I have fixed this for one layer, so that is easier to understand the overall architecture and simpler to follow. If you look at this input layer as indicated, the corresponding input layer, every primary input is fully connected with adaptive random weights between minus 0.1 to plus 0.1. Adaptive means the weight during it is trained, in the network weight is trained. Here we got 3 weight matrices. We have primary input to the input layer, that's the one weight matrix. we have input layer to the hidden layer, then we have another weight matrix, and we have another weight matrix from hidden layer to output layer. You got 3 weight matrices. The weight matrix from the input layer to the primary input to the input layer is we identified that as Win. The weight matrix from the input layer to hidden layer is identified as WH hidden, and then weight matrix from the hidden to output layer is identified as WOut. So if you take the every element here in the primary inputs are fully connected. That includes what is called a bias term. Bias term has got no inputs in any one of these cases. That's fixed, that corresponding to something like a threshold that we have studied in the threshold logic. There are no inputs for it. The output is always going to be fixed. That is going to be a 1. So every element, every layer, you would have the neural network inputs. In addition to that, we also have additional bias term as well. So if you look at the input layer, the SF stands for a summation function, TF stands for the transfer function, LR stands for the landing rule. Now all these 3 layers, they would use same weight summation function, and all of them use the same, that weighted sum, weighted sum, weighted sum, summation, weighted sum of the input activations. And then for the transfer function, you can have for all the 3 layers really, either you can use sine transfer function, you can use sigma transfer function, or tan H transfer function. For this, in this chapter, I have fixed the output transfer function as the sigmoid. I'll show you. I'll let you know why it is fixed in a minute, in just a few minutes. But for the input hidden layers, you can have either sine sigmoid or tan H transfer function. Whereas the learning rule is what is called the delta rule. It's also sometimes called the gradient descending algorithm that actually continues to reduce its overall network error, so that finally it results in a solution for it. If there is a solution, it will find a solution for sure, if you don't have a conflicting data. If it is a true measurement system, if the data is real data, then it will finally train the network for sure, and that is guaranteed by the backpropagation training algorithm. So what we have here is again each of the level you apply your primary inputs. Using these primary inputs, and when you multiply it with the input weight matrix, you are going to get the corresponding internal activations called I's, and the corresponding output activations called Yn. For the input layer, you would have the In and Yn, and using this Yn, you would compute the internal activation for the hidden layer, and using this hidden layer internal activations, you compute the corresponding activation for the hidden layer, and using this hidden layer activations, you would compute the corresponding output internal activations, and using the internal activations, you can compute the corresponding output activations. And once you compute it, whenever you train a specific data set, at the output you apply some primary input, and then correspondingly you would have the measured output values. The measured output value becomes your desired value, and the value, when you are doing the training, when you apply this input and finally compute the Y output, we have the desired value at the output and also the computed value at the output. And based on you keep training the network until the desired value and the computed output values are the same, or the difference between the desired value minus the computed value it gives you amount of error that we have in the network. So if you look at, so let's look into these various steps of transfer functions that are used with this network. Again, if you look for the various steps, what is a summation function and various steps of transfer functions. As you know, the summation function for any it is simply weighted sum of the activations. In this case, in general, as I indicated, the BP can have any number of layers. So the layer numbers in this case, for example, the primary input layer numbers are represented from 0 to n. 0 being this is like a L0, and then input layer becomes L1, hidden layer becomes L2, output layer becomes L3. Just in the simulation trace, I have given a specific name like a input layer, hidden layer, and output layer. But in generic representation, there are no such thing as the primary input. So this is indicated as a layer number. The layer number is indicated in this equations as a k. So this will be layer k equal to 0, k equal to 1, k equal to 2, k equal to 3. That is the layer number 0, layer number 1, layer number 2, and layer number 3. So the if you look for any internal activations for any layer, you take the corresponding activations and multiply the corresponding weights, and then that would give you the internal activation of a given element. That is y of I times w of ij. Again, wi is the source and j is the destination, and k is the layer number. So you start from the k equal to 0 and k equal to 1 to all the way up to k equal to 3 in this case. So they have w1 or w2 or w3. w1 is w in hidden layer weight matrix. K equal to 1 is going to be WH, that is the hidden layer weight matrix, and K equal to 3 is going to be output weight matrix W out. So in this case, the whenever you apply this weight matrix, you do the weighted sum of the activations. And once you compute your internal activations of each of the layer, that's I of j k. That means you would start from k equal to 1 and k equal to 2 and k equal to 3 in this case, because we got 3 layers. And then the j, each of the elements in the each element depends upon the number of elements that you have. That would be j, the number of elements which vary from 1 to nk. Nk is n0 is the number of elements that you have in the primary input. N0, n1 is the number of elements that you have in the input layer. N equal to 2 is going to be number of layers that we have in the hidden layer. N equal to 3 the number of elements that you have in the output layer. So, and then once you have that, internal activations are computed, then you compute the corresponding activations in each of these layers. Again, as you start from k equal to 1 and k equal to 2 and 3 and 4. In k equal to 0, you don't compute it because that is the input, that is the primary inputs. So that we already know. So in this case, again k is the layer number, w of ij, k of ij is that represents the weight from ith node to the in k minus 1th layer to the jth node in the kth layer. That is weight from layer 1 to layer 2. Obviously, I is a lower layer compared to the j, which is going to be the next layer. Ij is the weighted sum, yk is the activation, tf is the transfer function of the kth layer. That means tf, obviously k equal to 1, 2, 3. K equal to 1 is the tf1 is the transfer function for the input layer. tf2 is a transfer function for the hidden layer, and tf3 is the transfer function for the output layer. In this case, tf3 is a sigmoid that we have fixed. Nk is the number of elements that we have in each layer. L is the essentially layer number. in the network presented in figure 8.1, that is here. That's the we have the weights are going to be from W1, that's the 1, 2, and 3. One is W in, WH, and W out, and corresponding activation. Y0 represents the primary input, Y1 is Yin, Y2 is YH, and Y3 is Y out. And corresponding number of elements are N0, N1, N3. L is the number representation. That's go from 0 to 3, and K in this case varies from 0 to 3. X0, that's the Yin, and YW, and Y out. And these are the corresponding transfer functions for each of the layers 1, 2, and 3. Now the next thing is the transfer functions. So if you look for the transfer functions, in a sigmoid transfer function, as we indicated, it is the y is equal to e to the power of ig, and that is 1 by 1 to the power of e to the power of ig. That is 1 divided by 1 to the power of 1 plus e to the power of ig, which is same thing as 1 by e to the minus I dash times I dash. I dash in this case is the I times gain. I is the gain factor, and I is the internal activation that is computed. So if you take that value, that is 1 by 1 plus e to the minus ig, which is same thing as 1 by 1 plus e to the power of minus I dash to the power of minus 1. If you that is the value of the sigma transfer function, and if you take the derivative of this function and rearrange these terms, you would find that the derivative of this sigma transfer function is going to be y into 1 minus y. Quite often the gain is a fixed value, so quite often it is not considered because the constant value. So quite often when we apply what is called the error functions in the back propagation, we would use what's called the gradient. So gradient, that when you take the derivative of the function, sigma transfer function, its value of the gradient of this function is going to be y into 1 minus y. Similarly, if you take the sine function, the gradient is going to be 1 gain times 1 minus y square root of that. In case of tan h, that value of that is going to be 1 minus y square. So the gradient, again we will use this to compute what are called the delta functions or error functions. That means those error functions are going to be different for different types of transfer functions. So if you want to do a specific type of training, maybe we are better off fixing this, and then if you are doing programming. Otherwise the network becomes too complex. So what we have here is in this case, most of the applications that we have used in majority of the cases throughout this book, we have used sigmoid, because that is most frequently used transfer function in neural networks. It has got lots of advantages compared to other transfer function, and therefore it is appropriate to use that function. Again, in case of neurodynamics, here we would use the weighted summation function as I indicated earlier, and in this case we use sine, tan h, and sigma transfer functions for this network. We will use what we call the training algorithms. In the next section we'll look into what's called the gradient descending algorithm. What gradient descending means, it continues to reduce. that it will become a little more clear when you work out some examples. And then what is gradient means and what is gradient descending means. All that it means is as the network training progresses, the total network error, if you take the right gradient and reduce it, the error is continuously reduces irrespective of the measurements that you have. Now next let's look into the overall BP network, how it is going to look like, and compared to, for example, we have looked at the perceptron. Let's see that. Again, what we are going to look in is some of the topological examples how the network would get. We have seen generalized architecture, but how it would look like for a specific number of elements, and how overall network would look like. So if you go to pages, let me see this. Excuse me. If you go to these pages from pages 204 to 208, that's the second part of the chapter 8. There are 3 or 4 examples that are shown. Let's look into that. Again, if you look on page 204, that's the document C. Here you would see that this is this BP network is this is a 4-3-3-3 network. That is, we have 4 in the primary input, and 3 in the input layer, and 3 in the hidden layer. Again, we have this is a 4-3-3-3 BP network, indicating the 4 in the primary, 3 in the input layer, 3 in the hidden layer, and 3 in the output layer. In each of these cases, the one indicates circles indicates neurons, whereas the dots indicate just the primary input. They are not neurons. So big circles are neurons. For each of these network layers, we have a separate bias term. This is a B, and B. This in this case, the B term is indicated as a 0th term. And so if you indicate like 433, in addition to this 4, you would have a bias term 1. If you have in addition to 3, you would have a bias term here. In addition to 3 here, you have a bias term here. So if you look at the how the Win weight matrix is going to look like compared to the network, here you would see the in this case the for the W in weight matrix, we have 0 to 4 sources, and the destination are going to be 1 to 3. So now if we look for the see that Pi, these are the primary inputs. We got the 0, 1, 2, 3 and 4. That is the Pi 0, 1, 2 and 3 and 4. And the destination is going to be, this is IL, input layer. That is IL, IN, it should be IN. That is IN equal to 1, 2 and 3, corresponding to 1, 2, 3 elements. So the weight matrix is indicated as a source. This row represents the source numbers, and the column represents the destination number. For example, if you look at the weight, say for example, weight from for example, weight from 4 to 3, that is indicated as weight from 4 to 3, that is indicated as is 4 to 3 element 3. That weight is 0.83973. That's 0.893. The reason, one thing in this back propagation, all these weights are weights, activations, everything is represented to the 8th decimal place, 6 decimal places. A reason for that is the amount of weight changes that are made are very, very small, of the order of like vary anywhere between like 10 to the minus 1 to all the way up to 10 to the minus 6. That means if you don't represent to the 6th decimal place, you will essentially see all the zeros in, for example, for weight changes. So you need to have the high precision to be able to see, to be able to represent the weight changes and so on and so forth, and also amount of when you update it. It is, say for example, it is changed only like a 0000016. So unless you represent them to the decimal places, you don't see the changes clearly. So it requires high precision. Similarly, if you look for the weight, say for example from 0 to 3, that 0 to 3 means this is the weights from 0 to 1. That is the weight from 0 to 1, 0 to 2, 0 to 3. That is 0 to 1, 0 to 2, and 0 to 3. So the weight from 0 to 3 would be this one, that is 092. That's the weight matrix. So these are the sources and these are destination for WN. Again, when you go to WHL, we have got 0 to 1, which are going to be the source is going to be input layer, and the destination is going to be HL layer. That is the HL 1, 2, and 3. That is the inputs are 0, 1, 2, 3, 0, 1, 2, 3, and 4. So if you look for the what is the weight, say for example from 1 to 3, that is from the that is the input layer 1 to the HL layer 3. HL layer 3 to 1 to 3 is 0, 7. So that's what we have, the 0, 7 weight here. Similarly, when you go to the output weight matrix, the inputs are going to be HL elements, which is going to be 0, 1, 2, 3, 4, HL 0, 1, 2, 3, 0 to 3, and output obviously is going to be 0, 1, 2, and 3. That's OL 1, 2, 3. So the weight matrix are going from, say for example, the 3 to 2, 3 to 1. That is from element number 3, HL element, through the first element of the output layer. That is going to be number 3 to number 1. That's going to be 093. That's going to be that's 093 here. That's the weight matrix. So these are when the network is indicated here. Now we would specify the quite often for training. You don't know what the weights should be at the beginning. For a back propagation, you would start with some random numbers, with some small random numbers. Those random numbers are going to be anywhere between, as I already seen it, between plus minus 1.1 to plus 0.1. So those are going to be small numbers it starts with. So that's the network 3. For example, if you look for the next one, that's on the next page. Here, this one is a 544 BP network. That means you got 5 primary inputs, 4 in the input layer, and 4 in the hidden layer, and we got 4 in the output layer. Again, all these things are fully connected. What it means is every element here is connected to every element. What it means is input layer is going to receive, every element in the input layer is going to receive 5 inputs. Every element in the hidden layer will receive again 5 inputs, 0 to 5. Sorry, every element in the input layer receives total of 6. That is 0 to 5, which is 6 inputs. Every element here will receive 5 inputs. That is 0 to 4. Every element here receive again 5, which is 0 to 4 elements. Then you would see that's all fully connected. Again, it's a multi-layer. That's in this case is the 4 layers, and then the 3 layers is in addition to the primary input, and then it is fully connected. All the connections are only in the forward direction. Therefore, it's a multi-layer feed forward fully connected feed-forward network. Here is another example, that is the 0 to 5. That is again a 5 4 4 4 network. These actually indicates, if you go back and look into the text, this will show you the actual values that are there in the textbook. There it is represented in the text tables. Those tables are essentially represented in graphics format here. Like how much is if you go back and look at the simulation traces, you would see the network weights. Those are going to be like a network weight. Then actually goes to it performs like a forward pass. When it does forward pass it for a given inputs, what are the inputs, it shows what is the internal activation corresponding output activation for the input layer. Similarly here it will show the input activations and the corresponding activations of the hidden layer. And similarly here it will show what is the internal activations and the corresponding activations. So these are actual values in the text simulation traces, but this one is represented in the form of in graphics format. This is another one. Here again this is a 544 network. This one is again 4-3-3-2 network. The 4 in the primary input, 3 in the input layer, 3 in the hidden layer, and 2 in the output layer. So that gives you some example. These examples will illustrate how a BPA network varies. Obviously, you can change. You can have any number of primary inputs. You can have any number of for any given number of inputs. One thing that is quite often is necessary depends upon your x and y. The x is an input vector and y is an output vector. Usually the number of inputs that you need to have depends upon what your input vector size is. What is when you do the measurement, you know how many the number of inputs that you have, and that is usually have to match with the number of elements in the input layer. Similarly, when you do the measurement, you have the number of output measurements, and those output measurements usually refer to the number of elements in the output. So for example, you got 7 output variables, then usually you'll have 7 output elements corresponding to the 7 output variables. And this again the number of inputs equals to the number of elements that you have in the primary input vector. So for a given measurement thing, the number of inputs and number of outputs are depend upon the measurement input vector size and also output vector size. But you can have any number of input layer elements, and you can have any number of hidden layer elements. So that can be varied. Okay, now let's look into some overview of the BP network training. What is essentially the difference between perceptron versus say for example what is the difference between perceptron and the back propagation. Now let's go to the document A. There's a document A has got the overall network training. Network training overview. Again, if you go to document A, that's first page, and this is the look for the second page. So indicated in BP we have 4 layers: the primary input, input layer, hidden layer, and the output layer. 3 network layers. So basically, what we have here is the when you compute each of the elements in here, the the corresponding when you do what's called the apply the input to the network and then compute all the corresponding outputs, you need to do what's called a forward pass. That means you apply your primary input vector x, okay, then you compute your the in and yn here, and you use this yn to compute your in and yn here at the hidden layer, then you use this y to compute the value of said output. So that's called the one forward pass, that is applying x to compute value of in, then this use in to compute the corresponding yn here, and use this yn to compute ih here, then use this ih to compute the corresponding yh in the hidden layer, and use this yh to compute I out here, and then use this I out to compute the corresponding y out. So by the time when you apply a forward pass for a given input, you know all the internal activations and activations and also activations for each of the layer. What we are interested is the when you apply the input, what the corresponding computed outputs are. So whenever you do the measurements, you know the x value and also the corresponding value of the measured output values. The measured output values are indicated as desired values. So if you apply a input vector x1, x2, x3, when you do the forward pass, you know the corresponding y out 1, y out 1, y out 2, and y out 3. And these are computed values. And as per the measurement values, these are what are called the desired values. So the actual measured values are the desired values. These are the computed values. And so we have obviously once the network is trained, the computed values and desired values have to match. Okay, the first thing that we want to do is whenever you want to make weight changes to this network, when you want to make weight changes to this network, the weight change for any network will be del W, that is the amount of weight change that you want to make. Depends on the product of the three. One is the training coefficient, and depends upon the input activation, and also what is called the error function of the output layer. So this alpha, which is the training coefficient, is a fixed value. Whenever you set the training, that's fixed. And internal activations are nothing but when you perform the forward pass, you will know all the activations of each and every element. So if you want to weight change here, basically what you have to do is in generic representation, weight change is nothing but the alpha times y in times y delta out, that the input activation times output error function. For example, if you want to make weight changes from the hidden layer element to the output layer element here, we want to change weight from 1 to 3. That is the del weight change is going to be W of 1 to 3, and alpha, which is the training coefficient. And in this case, yn refers to the activation here. In this particular case is yh1 times the output error function. In this case, the error function of the element number 3, which is going to be delta out 3. So the R delta 3 here. So alpha is the training coefficient, delta out is the output error function, and yh is the input activation from the hidden layer. Based on that, you can do the weight function. Now that's what to be able to find weight changes in this layer, we need to have all the delta functions here, and we have to know all the activations here. Then we can make all the weight changes in this network. So if you want to make weight changes here, we need to have the delta of each element here and also activations of these elements. And if you want to make weight changes here, we need to have all the deltas here, and then we need to have the input activations. Of course, these are already known. So the thing that we want to do is the next part is the how do you compute what are called these error functions. Now this delta or the error function is given by what is called the delta error function is given by a product of the two, that is the gradient times the error. Now the gradient is nothing but the gradient of the transfer function of that particular layer. Now in this particular case we have fixed the transfer function to sigmoid transfer function. As we already seen, when we took the gradient of the sigma transfer function, it was y into 1 minus y. So that is the gradient of the transfer function of that layer. Then times the d minus y, that is the desired error. Error is represented by d minus y. D is the desired value, y is the computed value, that represents the error. So at the output, it's computing this delta function is very easy. When you perform the forward pass, you know the activation here, you know the activation here, you know the activations here. So the corresponding to that, you will be able to know all deltas. And also we also know from the measurement we already know the d value. So computing the delta function at the output layer is not it's very simple. Y into 1 minus times d minus y. All the y's are known through forward pass. Again, continuing on this, if you look at this for the layer which is between the hidden weight matrix of the weight matrix, can be done easily because we know all the delta functions at the output layer, which is very easy to compute. Y into 1 means we know all the activations, and also we know the desired value and also the computed value, and therefore we can find the delta through the forward pass. We all know the activations, and therefore the y is known through forward pass. Delta out is y into 1 minus y into d minus y, that is known, and therefore you can compute the weight changes here. The next the problem would be for the hidden layer and also input layer. Now when you come to the hidden layers, then the weight change that you want to make here, for example, that weight change is going to be again that weight change, say we want to go from here to here, we need to have the alpha here, that we need to have the yn, of course yns are known through forward pass, and then delta h2, that we need to have the delta h2. Now the thing is, how do we compute the delta functions for the hidden layers? Now the delta h1, for example, delta h1 yh1 1 minus h1, then if you use the same formula as d minus y, we have to have d minus yh1. But what is d? There is no such thing as a d here, because the desired values are known only at the output layer, and that's the biggest problem. The desired values are known only at the output layer, but not to the hidden and also the input layer. Same thing, that's going to be y into 1 minus y kind of yn. So neither we know the desired value at the input, nor we at the hidden layers. So we cannot use like y into 1 minus and d minus y for these elements in the hidden and the input layers. So the dh1, that's a d minus h1, d is not known. So error d minus c is not known here. The error d minus c is not known here. Y is known, but not the value of the desired value. D is known only at the output layers. The error d minus y, therefore what we have to do is there is a way to compute equivalent error, just like we have error at the output layers. that equivalent error is error d minus is computed as what is called the weighted sum of the output error function. So if you know the error here and we know error here, then we can compute equivalent error at these elements. So using these error functions we can compute, and also the weights that are connected here, we can compute what is called the delta function here. That is computed as error is computed as the weighted sum of the output error functions. So in this case delta h1 is given by yh1 into 1 minus yh1. That's not a problem. And then the d minus y part here for these elements will be given by the weighted sum. If you know what is weighted sum of the error output functions, weighted sum means this is this weight from here to here, the weight from here, and this weight times that delta, this weight times that delta, and this weight times delta out. That means that is equal to the weighted sum of the error functions are nothing but W out 1, that is the W out 1 times delta out 1 times delta out 2 times delta out 2 times delta W out 1 3 times delta 3. So if you multiply the corresponding element, that would give you what called the weighted sum of the elements. That is equivalent to d minus y here. Similarly, you can actually compute the delta I. For this element, if you want to compute delta weight functions, is nothing but that weight that's coming from here to here times that one plus this W times that delta plus times this W times that delta, and that would give the delta function. Of course, yh2 into 1 minus yh2, you have to multiply that one with. This should be repeated for each element of the hidden and also input layer elements. So one thing that we have to know is before you do for doing the weight changes for the network, you start from the output layer. Once you know all the delta functions here, use these delta functions to compute all the delta functions for each of the element here. Once you know all the delta functions for the hidden layer, then use this delta function to compute delta functions for each of the element at the input layer. So once you have the deltas for all the elements in the network, then we can go and find the delta weight change anywhere you want to. If the delta this y gives you the weight change here, this delta times this input activation times alpha will give you the weight change here. This delta times this input activation gives the weight change here. So the weight change in WH2 HL2 would be nothing alpha times YH1 times delta H2. Similarly, the weight change here is nothing but alpha times X1 times delta into and so forth. So with that, actually you'll be able to find the weight change for every element in the network. So the only part which is a little bit complex with respect to this one is the finding this error function for all these elements. Now this is conceptually this is a simple representation. Again, the error function delta out is given into y into 1 minus 1 and d minus y. What happens in this case is we are using these error functions to somehow compute the error functions here. So you take this error, somehow you propagate it back to the other lower level layers. That is computing this function like W out weighted sum of the errors. It is nothing but propagating the error from the output layer to the hidden layers. That is using this output layer, somehow we are finding out the error here. So the error is propagated from the output layer to the hidden layer. Similarly, the error from here, error of these elements are propagated to the input layer. So that's how actually the name, the error back propagation, known element error at the output layer are back propagated to the hidden layer elements. And similarly, error at the hidden layer elements in this case is computed. The hidden layer elements are back propagated to the input layer elements. That's how the name of the back propagation comes into this network. What is back propagated is the error from the output layer to the hidden layer, from the hidden layer to the input layer. How it is propagated? It is by computing what is called the weighted sum of the output error functions. So using delta out, delta I outs to all delta outs to compute all the delta H's, using all these delta H's to compute the delta INs at the input layer. And that process is called the error backpropagation, and that's how the name comes, backpropagation network. What is propagated is error, not anything else. So therefore, again here error said the hidden layer elements are computed as the weighted sum of the elements at the error at the output layer. So if you see this, the error, this once you know the d of dy, like for example, if you know the delta 1, delta 2, delta 3, say for example this is w1, w2, w3, you essentially compute the yh by y into 1 minus y, of course, times this one, delta 1 times w1, delta 2 times w2, and delta 3 times that, and that applies for any layer. Applies for all the hidden layer elements, and that applies for the input layer elements as well. Again, as you could see here, the error from the output layer is propagated to hidden layer as a weighted sum of the error functions, and the error in the hidden layer is transferred to hidden layer, and that's what is the sequence is called the back propagation, and that's how the name back propagation comes to name comes to this network. Now let's the next what we're going to do, this is some basic you need to understand conceptually what it means. Now if you what is the difference between the perceptron network and also the perceptron network for the, and what's the back back propagation. Now when you use back propagation in a perceptron, you have only one layer is trained. That means that means we know the error here, and then somehow multiply that with this one, you can weight changes. The input layer is not even trained, and therefore you don't have to worry about computing the delta functions, because if you have one layer, then the training is very simple. There is no such thing as back propagation. If a single layer exists, that would be it would be a problem only if you have multiple layers where all the network layer weight matrices are trained, and that's not the case in case of the perceptron. Perceptron, we have one the output layer, one input layer, but input weight layer weight matrices are fixed, and that they are not trained, and therefore there is no need to do this back propagation in case of the perceptron, and therefore it is very simple to implement. Next, what we are going to do is the BP training. Now let's look into when you implement the overall BP training, how we actually will go into step by step sequence by which we would implement the network training. This we can see in if you look into that's not 6A, sorry, I think it should be 6B. That's the chapter section A and 186 to 187. Let's look into this sequence of how the BP is trained. Now let's look into the BP training algorithm. Its algorithm is not a formula. It is a sequence of steps by which the network is trained. So if you look at the first thing that you want to do, this is implemented in step 1, step 2, step 3, and step 4. The way it is done is first actually The training are the computer error functions called deltas for each element in the network. How do you compute these delta elements? In this case, excuse me, I think I got the wrong one. Again, step-by-step training procedure, that's on page 185. Now, the training process, first step that you want to do to the overall network training is to start with the initialize the network with a set of small random weights. In this particular case, we're gonna we've got 3 weight matrices, the W in, WH, and W out. Each of these elements are going to be weights for each of the elements in these networks are initialized with the minimum of 0.1 minus 0.1 with the maximum value of plus 0.1. Then once that is done, then you apply. You do in a sequence. You apply set some kind of a flag so that whether the network is trained or not. So apply what you do is the first thing that you want. The next step that you want to do is you do what's called forward pass. Doing a forward pass means nothing but applying the primary input vector XP at the input of the network and compute the corresponding output vector WY out. So in this case, it's all actually done by one single formula here. That's in this case you apply the primary inputs, then compute the IN and YN, and then use HL elements to compute YL elements. So you start with the K equal, this is the K is the layer number, and so if you put K equal to 1, then that is you get all the summation. This part is the summation, and that is the transfer function. So the summation for each of these functions, if K equal to 1, you get all the internal activations for the input layer. If you put K equal to 2 and then actually run this summation function, you get activation for the hidden layer. When you put K equal to 3 and do the weighted summation function, you will get all the internal activation for the output layer. And then use this the corresponding IKs multiplied with the corresponding transfer functions 1 to 3. You'll be able to find the corresponding activations. So that indicates the computing the values of internal activations followed by the. Of course, in a computer program, you do this. It's not done one time. Actually, you do this I's first, then multiplied each of them with the transfer function to get the values of yi. Again, x in this case, when k equals 0, that represents the primary input vector. Again, the transfer function is a sigmoid in this case, we have fixed it. But whereas the transfer function for the input and hidden layer, that's a 1 and 2, it can be either sine, sigmoid, or tan H function. Then once that is done, we know the computed values. Based on the computed values and the desired values, we can compute what we call the RMS error for the network, which is nothing but the RMS, that is the square root, and that is the DI minus YI, or DI or DJ minus YJ square. Then root mean, then you RMS S square. Then you take the mean. Mean means the whatever the number of elements that you have at the output layer, divided by n3. That gives you the RMS. So we find out the square, then you find out the mean. Then R, that is the R part is the root. So you get this. So it gives you the RMS error for a given pattern. The algorithmic termination can be based on the TSSP, or it could be what's called the TSSTH. That is the most of the time you can use this. This is can be used as a network monitoring parameter with how far the network has come in terms of overall training. If you have a large TSSP, that means his network is far from trained. As it reduces to smaller and smaller values, you know how far it has come near completion. Again, if DM and AD is greater than that, yes, what you set up, there are two criteria. You can set up what's called a TSS-TH, like a 20%, 30%. If say, for example, if you put a TSS-TH as like a 0.2, what it means is for a desired value of 0, it trains every element for that element to be less than 0.2. On the other hand, if the desired value is 1, it trains better than 0.8. So, for example, if you have a TSS-TH of say 0.3, that is 30% error. That means for each d equal to 0, it will train to be make sure it is less than 0.3, and then the d equal to 1, it trains better than 0.7. You can put any smaller the number, it would be better. But if you want to have a quick results, in that case you can put a higher threshold error, percentage error. Again, this THH values varies from typical values would be like 0.1 or 0.2 or 0.3, 10% error, 20% error, 30% error. And the majority cases I have used 0.3 as a kind of default value. Similarly, once you have done, then based on that, once you have computed all your internal activations and then you compute all the delta functions for each element. Again, you start the k equal to, you see here it is k, you start from 3. That means you know output values for this is for k equal to 3, that's output elements. In that case, the delta function is going to be y into 1 minus y times d minus y, because we know all the y's and also with desired values are known. So for k equal to 3, which is the output layer elements, we can compute delta functions as y into 1 minus times d minus y. Whereas computing the error function for the hidden and the input layer elements, in that case obviously the value of could be either k equal to, first actually put k equal to 2, then you'll get all the delta functions for the hidden layer. So in that case, the error functions are computed as y into 1 minus y times the weighted sum of the output error functions. So you would see that error function for k equal to 2, you would use error function k equal to that is k plus 1, that is 2 plus 1, 3. So when you're computing second layer elements, error functions, you would use third layer elements. If I want to find the error function for the layer 1, which is the input layer, then you would use the delta 2, so which is going to be layer elements, second layer elements. So using the third layer elements, you would compute layer 2. Using layer 2, you would compute layer 1. So obviously, when you train it, you start from k equal to 2 and then k equal to 1. So they see this k is equal to, first you start 1. You cannot actually compute 1 and 2 because the 1 is not done. So first you know k equal to 3, then you compute k equal to 2 values, then you compute k equal to 1 value. That is the compute error function k equal to 3, then you compute the hidden layer elements k equal to 2, then you compute error function at the input, which is k equal to 1. Once that is done, then you compute the then you compute it is represented in one format, but in the simulation traces we got a separate network weight changes as a separate step. The next thing that is done is the del weight changes. Those weight changes are given by alpha times whatever the y of I times delta j. So you compute the weight changes for each and every element, then you add it to the old weights, and then you get the new weights. So this is the weight change, how much that you are going to make for a specific element. and then you add the old element values, then you get the new elements. So in this particular formula here, it's all represented in one step, but in simulation traces I have done it this one as a separate step, where the weight changes are indicated for every element in one step first. The next the step is old weights, and the new weight changes are made or updated to get new values. So this process is implemented in a two-step process. It's a lot more easy to understand. The once that is done, next one is the if you have a multiple pattern training, you can actually repeat that for all the patterns going from p equal to 1 to n. So once that is done, the next thing that you want to do is the overall network training. If you have multiple patterns, if it is a single pattern, it is going to be this one, that is di1y and divided by 1 by n3. It gives you the error for that one. But if you have the multiple patterns, in that case you compute the error for each pattern, add them up and divide by the number of patterns that you have. That gives you what is the total sum of squares cumulative error of all the total sum of squares cumulative error. And this is the network parameter that is used to do the network training monitoring, and that would actually do. So when you go into look into our the simulation trace, how it is implemented in this case, this step-by-step process is exactly followed in the simulation program, initializing the weights and then doing their forward pass, and then computing all the data functions at the output layer, then you finding the data functions for the hidden and input layer, then followed by finding the weight changes to the network, then adding those weight changes to the old weights to get the new weight changes. Each time you go through one change to the next one, these are all represented in terms of cycles. So in this is like a cycle 1, this is cycle 0. So you add the current cycle weight changes to the old weights to get you the new weights. Once that is done, you compute how much error is there. Then you actually, one thing that is listed is you have to test whether the network is trained or not. If the flag is equal to, then you go to set to. So flag, it means you need to test whether the network is trained or not. And once that is done, you will be done with. So we are gonna, the next step now, we're gonna go through a simulation program, how essentially work out some numeric example, how each and every step, what are the internal activations, what are the activations, and what are the what is the cumulative error, what is the corresponding values of the data functions and so forth. Data function, what are the output layer, what is the input layer, what is the weight changes, what is the updated values, and so forth. So that would give us a 100% understanding of the overall network training. After that, actually, once the network is done, then we are going to look into the what's called the network recall. Once the testing training is done, you can test whether the network is working correctly or not by doing what's called the testing. The testing in neural network, it is called the network recall. We will look into that little later. So let's next step is that is indicated in part B. That is working out specific example and going through that all these step 1 to steps 8 to implement the overall training. Okay, that's end of this section, and we will go to section B in the next part.